Hi, today we're going to be talking about RLC circuits. So RLC circuits are circuits we have a resistor, an inductor, and a capacitor. These type of circuits can be arranged as an RLC parallel circuit like this, where we have our three components in parallel. Like this, we have a resistor, an inductor, and a capacitor. And we can also arrange it in series, where my three elements are connected in series. So we have our resistor, an inductor, and a capacitor connected in series. Now, the important thing about these circuits is that they have one very special frequency, which is called the resonant frequency. The resonant frequency is the frequency at which the total impedance of the circuit is purely real, so that the impedance of the inductor cancels out with the impedance of the capacitor, making the total impedance completely real. This happens at one very particular frequency, which is called the resonance frequency. So, for instance, if we're talking about this parallel circuit, when we have the input voltage here, and let's assume that both resistors are the same value for simplicity, our impedance of my inductor is SL, and the impedance of my capacitor is 1 over SC. So we can calculate the total impedance of this circuit, which will be the series of this resistor with the parallel of these three elements. So I'm going to call the parallel of these three elements ZE. So my total impedance will be ZR plus ZE. And I can calculate the parallel with this equation. 1 over ZE is equal to 1 over R plus 1 over SL plus SC. So that ZE is equal to 1 over R plus 1 over SL plus SC. And my total impedance becomes R plus this quotient here. So now we substitute S by j omega so that we can look up of the frequencies. And my total impedance then looks like this. One over R plus 1 over j omega L plus j omega C. Now, this is a complex number, and we need to calculate to basically make the imaginary part equal to 0. So if these two go to 0, it doesn't matter how this quotient looks like, I will only get real numbers. If this is 0, I have R plus R, so I have 2R. Because then if the impedances of these parallel are 0, then I get have certain, they cancel out, so I only have R, the two R's there, and therefore my total impedance would become R plus R. So the point is we need to make these two numbers equal. So the sum of these two has to be 0 so that they cancel each other out. So we just write 1 over j omega L equals j omega C. So because when they're equal, they add each other out. And what we have here is that if I'm going to put the C down here and the j omega up there, so I get 1 over LC equals minus omega squared, because j times j is minus 1. Exactly. So basically my omega, my resonance frequency, let's call it omega R, will be 1 over square root of LC. So Yeah, when I subtract these two impedances is when they cancel each other out. So this becomes plus here, and my omega is real and positive, and this is the resonance frequency of the circuit. And it can also be shown that for a series circuit, the resonance is also 1 over square root of LC. So in the following videos, we're going to be talking about the properties of these circuits. We're going to look at the transfer function on all the different cases, and we're going to look at the step response and at the frequency response. Thanks for watching.